Another example problem. Light from a sodium lamp passes through a diffraction grating having 1,000 slits per millimeter. The interference pattern is viewed on a screen 1 meter behind the grating. Two bright yellow fringes are visible, 72.88 centimeters and 73.000 centimeters from the central maximum. What are the wavelengths of these two fringes? Okay, so these are measured to 4 significant figures, or 5, so they're very specifically measured, which is what astronomers do in terms of analyzing light. You need to be able to measure very precisely in order to differentiate between these wavelengths. So the problem tells us it's a diffraction grating having 1,000 slits per millimeter. This is in and of itself not D, because it doesn't have a unit of distance. It's telling us some number per distance, but we get D from this. There's 1 over 1,000 millimeters between each slit. We will want this in meters, so I'll do that conversion while I am at it. And yes, I should. And technically, we know this to 4 digits, the 1,000. So the distance between the slits is 1 micrometer, 1 micrometer. It is because these slits are so close together that that's why these wavelengths can be spread out and distinguished from each other. All right, so as far as the rest of the wording here, the interference pattern is viewed on a screen. That's the L. The screen distance from the slits is L. We're seeing 2 bright yellow fringes. Since these are fringes, these are both a Y1. One of them is located at 72.88 centimeters. I'll call that Y1A, I guess. Y1B is located at 73.000 centimeters. So we know the Y values, we know L, we know D, we're looking for wavelengths. So diffraction gratings are equations for diffraction gratings. D sine theta, where that's this theta of whichever order, is equal to m lambda, and then y sub m is L tangent theta. Okay. It's not telling us specifically that these are m equals 1. I'm going to assume that at first, but I will also need to double check for the wavelength answer I get and make sure it makes sense. If I look at the test notes, it tells me yellow is approximately 570 nanometers. If my answers I come up with for these wavelengths is not approximately that, then I need to try m equals 2 or m equals 3. All right, so for 1A, we're trying to get back to wavelength. Since I am assuming m equals 1, we can say d sine theta 1 is equal to the wavelength. Y1, the location of the bright spot on the screen, will be L tangent theta 1. We know L, we know where these are on the screen, So we know y and L. That means we can solve for theta in the bottom equation. Once we have that, we do know d as well. We can use the top equation to find that wavelength. So tangent of theta 1 using this first y1 value will be y1 over L. Now I do want to watch my units here. These units need to cancel in order to take the inverse tangent of both sides. So inverse tangent of the 0.7288 gives me 36.08 degrees. I can now say this wavelength would be d sine theta 1. Calculated d above on the right from that 1,000 slits per millimeter. So wavelength is d sine of this angle. So let's see what wavelength we get. So sine of that angle times 1, oh dear, -6. So I'm getting 589. So I can go to 4 digits. Okay, so I'm technically getting 588.979 nanometers. This is in the visible region. It's a bit higher maybe than we expected in terms of that 570, but that 570 is an approximation. So one of the wavelengths of light is 589.0 nanometers. We do know this to 4 significant figures because these measurements are very accurate to 4 or 5 for the 73. So that is one of the wavelengths. The wavelength for the other one, I called that 1B. Same set of equations, but 0.73 meters over the 1 meter gives us a slightly different angle of 36.129 degrees. So it's not hugely different because of that really tiny spacing between the lines. We can distinguish that. Sine of this new angle, this wavelength ends up being 589.61. So to 2 sig figs, 589.6 nanometers. So very, very small difference in wavelength. Sorry. My dog really wants to play. So we get a very, very small difference in wavelength, but these diffraction gratings, because there's so many slits and because they are so close together, it can separate these wavelengths that are very close to each other and separate them out so that we can distinguish between them. Each element has unique wavelengths that it emits when the gas is excited. Essentially, you apply a voltage to it, it excites the gases, and in turn they release light.